So for today's topic, we're going to focus on other techniques for evaluating limits besides just being able to look at a graph or a table of values for a given function. So this is where all the algebra stuff is going to come into play. So our first topic of discussion is direct substitution. So you've heard this phrase before in class and in the previous video. This is really the simplest method of evaluating limits, and really anytime that we're not looking at a graph or a table to come up with our final answer, direct substitution is really how the problem is going to end. It's the first method that we're always going to start off trying. Sometimes it will work, sometimes it won't. But when it doesn't work, we're going to have other methods to employ and trying to fix the given function. And then hopefully, after trying that one time, we'll be able to use direct substitution again to finish the problem out. But the idea behind direct substitution is as long as we're working with a well-behaved function or one that's defined at the value of x that we're looking at, then the limit as x approaches that value is simply the function's value there. Or, in other words, the limit as x approaches c for a function f of x is really just equal to the value of the function f at c. The only exception to that is a oddball kind of function that looks like this guy. So we would have a function with a given hole, but then elsewhere we would have an additional point defined at that particular value of x that we're concerned about. The reason this is an exception is when I would plug that value of c into the function is defined up here at this point, but the limit is actually down here at the hole. The reason why that's the exception or why we're not too concerned about that is that's not a naturally occurring situation, and it'll be super easy for us to tell when that particular situation is occurring because the only way that we can create that situation is with a piecewise function. So we'll know that that's going on just simply by the way the equation is defined. So when we try direct substitution, again, it's really just we're working with a really easy, well-behaved function, and to evaluate, we just simply try plugging the value of x into it. So all these examples that we're going to take a look at down here are all of these really well-behaved functions. Not all of them are the easiest functions to work with, but around the particular value of x that we're concerned with, they're well behaved. There aren't any real issues. There's no break discontinuities, no asymptotes. The functions themselves may have those things elsewhere, just not at the point that we're concerned with. So let's just dive in and try a couple. So x squared minus 8, I'm going to remind you guys what the graphs of these look like as we go so that you can kind of start brainstorming that in your head along the way. So for some of these, it's pretty simple to imagine what the graph looks like. X squared minus 8, that is the parent function, quadratic function shifted down 8 units. So it's a polynomial. All polynomials are well behaved, domain of all reals, so no issues to worry about. So we can just directly substitute 2 in for x. So I get 2 squared minus 8 is going to give me -4, and that is where or a point down here at 2, -4 on the function. So that's it. We just plug the value in. Next one, limit as x approaches 2 of the function square root of x plus 7. If you remember, square root functions are like the springboard graphs. This will be a horizontal shift to the left 7 units. So its vertex is back here at -7, and then it launches out up and to the right. So this is another well-behaved function on its domain. There are no holes, asymptotes, no breaks, nothing crazy on this. It just doesn't have an all reals domain. But from -7 to infinity, it's a well-behaved function. So we know it's defined at 2. There's no holes or extra points or anything like that. So we can just plug 2 in. We get the square root of 9 or 3. All right, next one. This is a rational function. So rational functions are definitely more difficult than polynomials or square root functions. But around x equals 2 for this guy, there aren't really any issues. So for this particular graph, it looks more difficult than what it is, but the domain would be everything but not x cannot equal -3 because there is a vertical asymptote at -3. If I compare the degrees, I've got same over same, so it's a ratio of their coefficients, which would be 1 in this case. So this function has a horizontal asymptote at y equals 1. I can do a quick test point of x equals 0, plug it in here. I get negative 1/3, so I know that the y-intercept is down here, so I know that the function is somewhere in this section and then somewhere in this section. So knowing all that, again, it's not a well-behaved function everywhere because obviously there's a vertical asymptote that would cause us some issues, but at x equals 2, on this isolated portion of the graph, there are no issues. So I can use direct substitution. So if I do that and I plug 2 in, I get 1 in the numerator, 5 in the denominator. So on this function, there is a point at 2 1/5. Okay, now the next one. So we have a cubic function. I don't know offhand what this guy looks like. I do know what the end behavior is doing. There's a positive leading coefficient for an odd degree function. So I know somewhere down here, the graph's going here. Somewhere up here, it's going up forever. But in the middle, I don't really know exactly what's going on. I know there's a y-intercept at -3. So it probably looks something like that. But that doesn't really tell me the full picture, and that's really just an estimation of what it would look like. But just to remind you, this is also a polynomial. Remember, quadratics, cubics, quartics, all those guys are polynomials, which means their domain is all real, so we don't have to worry about any domain issues or anything crazy going on. So again, it is a well-behaved function. So I can just simply plug 2 in there. So I get 2 cubed plus 4 times 2 minus 3, so 8 minus 3 gives me 13. So that is our limit. All right, now next guy, e to the x, exponential functions. These are also well-behaved functions. They always have a domain of all reals because I can raise any number to any power, I can raise a positive number to any power that I want to without any issues. If you guys remember, exponential functions have a horizontal asymptote before any transformations. They have a horizontal asymptote on the x-axis. So remember, e to the x looks like pretty much all the other exponential functions, just going to grow very steadily, faster and faster and faster as we go. So for this one, there's not really anything crazy here. Again, if there's a domain of all reals for the function, we're guaranteed not to have any issues, so we can just simply jump right into plugging it in. So in this case, we get e squared. You will get into the habit of leaving things in terms of irrational numbers. So radicals that don't break down any further, base e expressions, same thing with pi's. We can get a decimal value for those, but it's not really worth our time in most cases. So just get used to the idea of leaving things in terms of e when they show up. All right, now for this next guy, natural log of absolute value of x plus 4. You guys have seen natural log functions before. So if this was just the natural log of parentheses x plus 4, that's the natural log of x function shifted to the left 4. So it would look like this guy. Okay, but when we see these absolute value bars put around the argument of a natural log or any logarithmic function, what that's doing is it allows more values of x to be used as inputs, because one of the rules for logarithms is the argument has to be strictly positive. It can't be 0 and it can't be negative. So the absolute value bars make all of the values that we get in that argument a positive value. So now the only issue we have to worry about is the value of x that makes the argument 0, which in this case is -4. So what happens is the natural log of the absolute value of this, it's actually just a mirror image on the other side as well. So if I were to plug in -3, I get natural log of 1. And if I have the mirror image on the other side of x equals -5, I also get +1 as the argument because of the absolute value bars. So when you see those absolute value bars, it's really just introducing more values of x that we can have as input values. So in this case, as long as it's not -4, any value would be a well-behaved portion of the graph. So in this case, I can just plug 2 in, and so I get natural log of 6. Now we're going to take a look at some properties of limits. So before we can really dive into the algebra side, we need to just kind of go through some of the basics. So remember, when we try to evaluate limits, a lot of times we end up using direct substitution, which is really just evaluating the value of a function. So what we see is a lot of properties that exist with functions also exist with limits, because they kind of work in tandem. When we evaluate a limit, we're looking at what's the value of the function approaching as we get really close to a particular value of x. When we evaluate a function, it's just what does the function actually equal when we plug that value of x directly in. So it's a lot of the same kind of math, which is why a lot of these properties exist for both. So to explain these, we've got two functions, f and g, each being evaluated as the limit of x approaches c for them. So the limit for f we refer to as L, and for g of x, it is k. But basically the way these work is we're just kind of manipulating the functions as we go, but also taking the limit of the new expression. So scalar property, scalar means we are multiplying something together. So if I take an original function and multiply it by a number out in front, well, all that does is just multiply the limit of f by that same value, so we end up with b times L. So this would be like if I take the limit as x approaches 2 of the expression x, that's a well-behaved function, so I can use direct substitution, so that limit would be 2. If I evaluate the limit as x approaches 2 of 4x, well, that's just 4 times 2. So it's a way of manipulating the y values. So if all the y values grow by the same factor, then so will the limit of those y values. Sum or difference property, this one's pretty basic. If I take two functions and add or subtract them together and then evaluate the limit of that expression, it's like adding or subtracting the limits of those two functions individually. So we get L plus or minus k. Product property, quotient property, exact same situation as the sum and difference. The only difference or exception here is, remember, with division, we can't divide by 0 ever. So the only stipulation here is the limit of g of x as x approaches c can't be equal to 0. So that k value can't equal 0. Otherwise, we would get a undefined expression. Power property, same idea. If I take the a known function, raise it to a power, then whatever the limit of that function raised to that power is our result. The trickiest of all of these is a composition function. So the reason why this is tricky is because when we compose functions, you're making the output of one function the input of another. So this expression f of g of x, so f of g of x is like a three-step process. So first, an x value goes into g of x. Then an output value comes out. But that output value goes into the function f of x as its new input. And then we evaluate or find the output value of f of x. Okay? So it's a three-step process. So when we think of that through the lens of limits, we need to first evaluate the limit as x approaches c of this inside piece. So again, we're not actually evaluating g of x, although that may be the route we take with direct substitution, but we're still evaluating that limit. So that's why it changes notation to this guy. So whatever the limit of g of x as x approaches c is, that answer then becomes the input to f. And then we go through a similar process. So we want to try and find the value of f, and sometimes that requires us taking another limit of f as x approaches that particular value that's getting plugged in there. So the big stipulation here, and we're going to see some examples of this here in a second, is that f has to be continuous at the whatever the output or result of this limit for g of x is. If it's not, then we run into some issues and we have to handle it in a particular way. So let's try applying some of these limit properties. So to do this, we've got some information here. So first off, I've got a graph of f of x. Shown here, all kinds of weird issues going on here, so we got to pay attention to some of that stuff. And then I've got three individual limits. So I don't have an equation for f or g, but I do have some either graphical information or limit information to help us with some of these limit expressions down here. So we're just going to kind of go through, use the properties to help us along the way. So even though the properties are listed individually, we can combine any of those that we want to, just like you can combine multiple operations to create one function. So for this first expression, we want the limit as x approaches 1 of 4 times f of x minus g of x. Now, every time we do this, we are using these properties, but it's not the case where we have to rewrite them every single time. Because if I needed to do that here, I'm using a scalar multiple of f of x, so I would need to break that out in front. And then I'm also using the difference property, so I would have to take the limit of g of x and subtract that answer from whatever I get here. So a lot of this is going to be done in our heads. This is pretty simple math once you understand the idea or concept of a limit in general. So we don't necessarily have to write this out every time. It's really just a matter of understanding the properties that we are executing here. So first limit we're going to take as x approaches 1 of f of x. So on this graph, as we approach 1 from the left and the right side, we are approaching a y value of 1. So I would get 4 times 1 minus, then the limit as x approaches 1 of g of x is given to us as 2. So this whole expression has a value of 2. That's it. So in the next one, limit as x approaches negative 1 of the expression f of x plus 4 over g of x. So same idea. The limit as x approaches negative 1. So from the left side on f, I'm approaching 3. From the right side, I'm approaching 3. Remember, even though there's a hole there, it doesn't affect the outcome of this limit. So the limit of f of x as x approaches negative 1 is 3 plus 4. So I can add values to it with no issue. And then the quotient rule that we're using here has g of x in the bottom, and that limit is 4. So all told, we get 7/4 as the answer. So again, the idea here that's kind of hiding in the background, if I actually had the equations needed to create f of x or whatever equation is used for g of x, if I were to take those actual equations and the expressions from them and do all this math and create a new fraction or a new function, and then use direct substitution or these other new methods we're going to look at to evaluate these limits, this is what the y values for that new function or new expression would be approaching. But when we're using the function names, all of that math is kind of in the background. All right, next one, product property. So we're going to take the limit as x approaches 1 of f of x, which we know is 1, multiplied by g of x, which is 2. So that's pretty simple math. All right, and now here is the difficult one. So we've got a composition function. So again, the idea is to evaluate this, I need to know what's going on the inside first. So I'm going to actually rewrite this as the limit as x approaches negative 1 of the inside function first. So we need to evaluate this. So the limit as x approaches negative 1 of g of x, they gave that information to us as 4. So now we need to take this value and use it as an input to f. So I am trying to evaluate f of 4, but the rule is the only way that I can do this easily is if this function, the outside function, is continuous at the value of x that we are trying to input. So I need to go to the graph of f and locate x equals 4 on the graph. So this is a smooth curve. There are no jumps or holes or anything like that. So we know that this function has a defined value of 2. So the way this limit works is if I continue to use values of x closer and closer to negative 1 and substitute them in here, when I substitute them into g of x, the y values or the outputs are getting really close to 4. So as I take those results, 3.9, 3.9999, and substitute those into f, those results are going to be getting closer and closer to 2. So that's the idea. So this expression has a final value of 2. All right, let's try another composition one. This one's a little bit trickier because it's a function composed with itself, but the rules don't change. The process doesn't change. So first I want the limit as x approaches negative 1 of the inside function, which is f of x. Okay, so now we need to go to the graph. So the limit as x approaches negative 1 is 3. So we need that result. So normally, like we did on the last one, I would take that value and try to evaluate the function, the outside function, at 3. Well, when we go to x equals 3, on the graph, we see that this function is not continuous. We have a break in the graph. If I was tracing, and I have to jump up here to the next portion. So that means that I can't actually evaluate this the same way. So there is no answer to this right now, because when I chose, or when I evaluated this limit, again, the idea is you're picking values of x really close to -1, either from the left or the right side. And what this expression is saying is, as I do that, I am approaching 3. But because this graph is discontinuous at x equals 3, I need more information about the first limit. So it's not just about what y value you are approaching, it's actually about how are you getting there. So as you see on this graph, from both the left and the right side of -1, we are approaching 3. But on both sides, you are approaching it from y values that are smaller than 3. So 2.5, 2.7, 2.9, 2.999. Same thing on the other side. We're working our way up from the negative side of 3. So I need more information here. I'm going to put a little negative up there in the corner. Remember, we've seen that before with x values, but we can do the same thing with y's. It's giving us a direction. So I can now read this or interpret it as the values of x get closer to -1 on f of x, the y values are approaching 3 from the negative side. This allows me to now, instead of trying to evaluate f of 3, we can use a limit approach. So I'm going to use this result as the new value of x that I used to take the limit of the outside function. So if I now go to the graph of f and try to evaluate the limit as x approaches 3 from the left side, that would give me a limit of -1. And that is our final answer. So basically, what can happen with these composition expressions, sometimes they work out super easy and nice. If we were to have a result where the function is continuous at the value of x we're trying to plug into the outside guy, then it's no-brainer. We just figure out what the value is, what the limit is, and that is our answer. But when the function is discontinuous, we have to go back and establish a direction on how we approach this y value. So the options are, you could be approaching a value of y from the bottom side, which would be a negative, or it could look like this, where you are approaching that value of y from the top of it on both sides. In that case, you would be approaching it from the positive side. Or we could have an even bigger issue where you are approaching it from different sides. If we were approaching it from different sides, one side from the bottom, one side from the top, and we tried to do this same scenario here, that would be a case where this limit does not exist, because from the left side you're approaching one value, and from the right side you're approaching a different value. So basically, when we do these composition problems, there are three scenarios where we where the function is not continuous at this second value. So these are the three scenarios that could exist. So these first two, you would be able to come up with a final answer. This guy, we would look for the value as we approach it from the left, this one from the right. But then this guy would be a case where the final answer would be does not exist, because you would be trying to approach it approach two different values on either side. So these composition ones are definitely the trickiest out of all of these. They're really the only ones that are going to make you pause and do some thinking. All right, so for the next one, limit as x approaches 1 of the expression 3 times f of x quantity squared. So let's first find a limit as x approaches 1 again. That was 1. So we're going to take 3 times 1. Oops, forgot my brackets. 3 times 1 is 3, and 3 squared is 9. All right, next one. Limit as x approaches 3 of g of x. That was one of the values given to us up here. That's -3. So I have -3 minus 5. And then limit as x approaches 3 of g of x. Well, that is an issue. We don't have a limit as x approaches 3. There's no direction given to us. So because there's no direction given to us, there is no way for us to evaluate this bottom limit. So if any part of a limit expression does not have a limit, or the limit does not exist, or the limit isn't infinite, we have to take that into account. So because this bottom does not exist, there's no way for us to evaluate this entire expression. So our result would just be the limit does not exist. And then our final one, limit as x approaches -1 of this big expression. So basically just evaluate each part inside. So for f of x as x approaches -1, that limit is 3 plus, and then for g of x as x approaches -1, that is 4. So from there, it's just order of operations. 3 plus 4 is 7. 7 squared is 49, and 49 times 2 is 98. And that is our final answer. Now we're going to talk about what happens when direct substitution fails. So this is going to be the algebra-heavy portion of this section. So whenever we try to evaluate a limit without the aid of a table or a graph, your first attempt should always be trying to use direct substitution. If it's a well-behaved function, then we can just simply plug the value of x that we're evaluating the limit at into the function and see what we get. Sometimes this result's not straightforward, so we have to have other options though. So it can be difficult to identify which strategy should be used when trying to evaluate a limit, but this flowchart does a nice job just kind of guiding you through that process. So no matter what, though, our end goal is to be able to use direct substitution or our properties from above to evaluate the original limit. So to do that, sometimes when you try direct substitution at first and it fails, we have to rewrite the original form of the function so that direct substitution is possible. And we can do that using factoring, rationalizing the expression. So that's when we have radicals in there, so square roots, cube roots, that kind of stuff. And then some of our trig identities from pre-calculus are going to come back into play now. So if none of those are possible or fruitful, worst case, then we have to go try and graph it and or use a table to evaluate the limit. But most of these, we're going to be able to do some kind of algebraic manipulation to it so that we can evaluate. So on your first try, when you're going through this flow chart, again, first step is always trying to evaluate the function at the value of x. So that is direct substitution. So your outcome, there are 3 possible things that can happen. So first off, I can get a number. So while this may seem a little redundant, it is important to remind everybody when you get a fraction that has 0 in the numerator and any non-zero value in the denominator, that is a number. That results in 0. For some reason, that's always a result that can trip people up because of some of these other results that we get. But 0 divided by anything that's not 0 is 0. So if you get any other number or 0, then you're done. That's it. Direct substitution worked. And again, the only way that we get that is if the function is well behaved at that particular value of x. Second option, you get 0 over 0. Okay, this is referred to as an indeterminate form. A lot of people think 0 over 0 means 0 or is equal to 0, but that's not the case because now that we're working or transitioning into calculus, what we have to really think about are infinitesimally large and infinitesimally small values. So 0 doesn't just represent nothing. It represents quantities that are so tiny, they're indistinguishable from 0. So it's not that they actually are a value of 0, they're just really, really tiny. And so when we have a ratio of a really tiny value to a really tiny value, it's hard for us to determine which one of those is bigger than the other and see which or how their ratio actually evaluates. So that's why when we get a result of 0 over 0, it's referred to as an indeterminate form. Now, later on down the road, we're going to take a look at some other indeterminate forms, things like infinity over infinity, 0 to the 0, infinity to the 0, 0 to the infinity. There are a whole bunch of different kinds of indeterminate forms, values where the expressions just don't really have any meaning to us, and so we have to do further investigation to try and fit it to a form that does have some kind of meaning for us. But for now, the one we're going to focus on is 0 over 0. When you get an indeterminate form, this is where you have to go into your bag of tricks and try all the different things that you know how to do to an algebraic expression to rewrite the original function in a new equivalent form, and then we repeat the process. That's what this big blue arrow is telling us. So when we get an indeterminate form, we're going to try and fix it, and then go back, try direct substitution again. If it works, great, we'll get a number. If it doesn't, then we've got one of these other options, and we're going to have to kind of repeat the cycle. The third option is you get something that's not 0 divided by 0, or you'll see me commonly write this as some number divided by 0. Again, we can't think of 0 as always just representing nothing. So what this expression is really saying is as x gets really close to a, the numerator is going to be approaching some value, some non-zero finite value, but the denominator is approaching 0. It's not equal to 0, it's approaching it, which means you're taking some number and dividing it by smaller and smaller parts. Well, a simple investigation can explain what exactly that means. If I take 1 divided by 10, it's 0.1. 1 divided by 9 is 0.11, repeated. 1 divided by 8, 0.125. I'm going to skip a couple. 1/5 is 0.2. 1/3 is 0.3 repeated. 1/2 is 0.5. So as the denominator is getting smaller and smaller and smaller and approaching 0, you see that the value of the fractions, or the ratio, are getting larger. Now, these aren't getting real big, but if I take the denominator and make it 0.1, well, now that has a value of 10. 0.01 has a value of 100. So as they get, and 0.01 is still pretty far away from 0. There's an infinite number of numbers between those two, so it can get really, really close to 0. So the closer we get to 0, the larger this value of the fraction is going to grow. So when we see a number divided by 0, it's really another way of representing the quantity of infinity. So when you guys see a non-zero number divided by 0 in your brains, you need to be associating that with the value of infinity. Now, if this was a negative number divided by 0, or the number on top is positive and the value of 0 is approaching 0 from the negative side, then it's possible we are approaching negative infinity. But the idea is a non-zero value divided by 0 will be approaching some form of infinity. This happens when the graph has a vertical asymptote at a particular value of x. So if you guys remember from Algebra 2 or pre-calc, that's one of these guys. The limit as x approaches a of f of x is not a finite number. So this is a case where technically it does not exist, but if we can gather more information and actually determine what kind of infinity we're approaching, then that's really important to us. So that gives us a clue as to what the graph's going to look like. So that would be information we would want to provide. But those are the 3 outcomes. So every time that we do one of these limit problems with direct substitution, you should be getting one of those and then use that to determine your next steps if you have any. All right, so now we're going to take a look at all these different techniques that could possibly pop up. But I want you to keep in mind and notice for all of these, our first step is always going to be using direct substitution, because we might get lucky and it might be a simple problem where we can get a final result right off the bat. So let's dive in and try some. So the first one, limit as x approaches 3 of the function x squared minus 9 over x squared minus 6x plus 8. So direct substitution yields 3 squared minus 9, or 0. And some people think that as soon as you get 0 in part of it, that you're finished. Always make sure that you evaluate the denominator, because it's never a guarantee that you know exactly what the final outcome is going to be. So in the denominator, 3 squared would be 9 minus 18. 6 times 3 is 18 plus 8. This yields -1. So I end up with 0 divided by a number that's not 0. So that final result is 0. And again, this is the one that I was describing earlier, that some people mistake this as either the indeterminate or the infinite form. But remember, 0 parts of a number just represents a 0. So, or in other words, this top is, as x gets closer to 3, the top is getting close to 0, the bottom is approaching -1, so their ratio equals 0. So that's it. This is a easy case. This is that first track on the flow chart. So that's always why we want to make sure that we try direct substitution first and we don't mislead ourselves to accidentally doing something differently, especially when we have polynomials on top and bottom. You guys are going to see some of these other problems require us to factor. Don't automatically start doing that stuff just because it looks like it's a quadratic function that you recognize can factor by difference of squares. Yeah, that's true, but just because it factors doesn't mean that it'll have common factors that will reduce out and yield more results. So you have to be very careful not to do more work than what's necessary. All right, second one. Limit as x approaches 3 of x squared minus 9 over x minus 3. Try direct substitution again. So 3 squared minus 9 is 0. 3 minus 3 in the denominator is also 0. So this is our indeterminate form. This is your red flag. When we get indeterminate form, this is where we need to go back to the original function and think of ways to rewrite it. Anytime that you've got polynomials involved, factoring is an option. So let's explore that. X squared minus 9 would factor to be x plus 3, x minus 3. Our denominator is a linear expression, so there's no factoring involved there, no GCF to be pulled out. As soon as you see our finished factoring, look for common factors in the top and bottom. And in this case, x minus 3 is a common factor, which means they cancel each other out. Anytime that you cancel out a common factor in the top and bottom, what you are doing graphically is identifying a hole on the graph at the corresponding value of x. So in this case, the factor was x minus 3. So what we essentially did was remove a value of x that was restricted, and that would be positive 3. So this hole on the graph of this original function is at x equals 3. By removing that factor, you are now left with the expression x plus 3. That is the function that we will actually evaluate the limit of now. So the limit as x approaches 3 of x plus 3. That is something that I can use direct substitution for, and I get 6. This result, that answer here, is actually the y-coordinate of this hole. So by doing all of that, we evaluated the limit, but we also know the coordinates of that hole. So this original function behaves just like this function, except it has a hole at 3, 6. So we know what the graph of x plus 3 looks like. It's just a slope of 1 with a y-intercept of 3. But now I know an additional piece of information. It has a hole at the coordinates 3, 6. That's the power of being able to evaluate these limits and knowing what we're doing here. All right, next one. Limit as x approaches 3 of x squared plus 9 over x minus 3. Notice the similarities between these first three functions, okay? But again, direct substitution. For the numerator, I get 3 squared plus 9. That gives me 18. And the denominator, 3 minus 3, gives me 0. So from the first three, we've actually seen an example of all three possible results. 0 over a number is 0. 0 over 0 is indeterminate form. You have to fix it. But a number, a non-zero value divided by 0 yields infinity. So again, you could say does not exist, but what you're really telling us, or what we're really learning here, is that this graph has a vertical asymptote at x equals 3. Now, what the rest of the graph looks like after that, we'd have to do a little bit more investigation, but you know for sure that this graph has a vertical asymptote at x equals 3. All right, next set. I'm going to take the limit as x approaches 3 of x squared minus 9 over x plus 3. So again, another similar one. So for this one, when I plug 3 in, I get 3 squared minus 9 is 0. And on the bottom, 3 plus 3 is 6. So again, another result of 0 over a number, which leads us to 0. So this one seems a little bit redundant. Like what was the point? We already know what x squared minus 9 yields as x approaches 3 after all these other examples. But the reason I put this one in here is after doing some of these other problems, some people may look at this and immediately jump to factoring this numerator. So the numerator does factor, and it actually shares a common factor with the denominator of x plus 3. But if you do all of that math and cross those common factors off and then go to evaluate the limit, in this case, it's going to yield the same thing. 3 minus 3 still gives me 0. But you did a lot of extra work to get to that result. And sometimes doing that extra work will actually lead you astray, and it could tell you an incorrect result. It could tell you that the limit does not exist or the limit is a different value. So you want to make sure that you're not doing work that is unnecessary. And that's why it's really important to always follow the flow chart. We try direct substitution first, then factor or do that manipulation if it's necessary. In this case, it's not necessary. So it would be a waste of your time to go through all that process. All right, next one. Limit as x approaches 3 of x squared minus 9 over x squared minus 6x plus 9. So direct substitution first, I get 0 up top. And then the denominator, I get 9 minus 18 plus 9, which gives me 0 as well. So another indeterminate form. So we need to factor. We know the top is x plus 3, x minus 3. The denominator, that is actually a perfect square trinomial. That factors to be x minus 3, x minus 3. So again, I factored. I did some algebraic manipulation. Now we're going to look for common factors to reduce. So this one is tricky. So there are 2 factors of x minus 3 on the denominator, but just because there's one up top doesn't mean that both of these guys in the denominator reduce out. This would be similar to the idea of 2 over 12. 12 can be broken down to be 3 times 2 times 2, but only one factor of 2 reduces out from each of those, which is why 2/12 reduces to 1/6, as you guys all know. So we can't cancel out both of these factors. So there's one that's sticking around. So the new form of the function that we are going to try to evaluate the limit of is x plus 3 over x minus 3. So again, the idea of this indeterminate form, the reason why it's an issue is because there is a factor in the numerator and denominator that when multiplied all together make both of them equal to 0. Both can't be 0. The top could be equal to 0, and the bottom could be equal to 0, and we get a final answer. But they both can't be equal to 0. That's what leads to this indeterminate form. So by removing that common factor out of top and bottom, that's what's going to allow us to continue the problem and get to a final answer. So now when I substitute in, I get 6 in the numerator, 0 in the denominator, which again is a form of infinity. So that must mean, in this case, we removed a factor, but then it's still an issue. So this function would actually have a vertical asymptote. So even though the value of x we removed was x equals 3, and that is still the value of x that produces infinity, you can't have a vertical asymptote and a whole at the same value of x. The vertical asymptote takes over. So this guy just has a vertical asymptote at x equals 3, and then we've got some other stuff going on here. Okay? All right. Now on to some radicals. So this is another method that we have to apply here to be able to evaluate. So obviously when we have radicals involved, they're not polynomials. So we can't just simply factor top and bottom and fix this guy. But let's first check to see if it's even necessary. So limit as x approaches 4 of the function square root of x minus 2 all over x minus 4. So if I plug that in, square root of 4 is 2, minus 2 is 0, 4 minus 4 on the bottom is 0. So yes, it is necessary. So when you have radicals involved, the reason that, again, we can have 0 in top or bottom, but the reason that 0 is in both is because of this radical part. So this is called rationalizing the numerator. You guys have seen rationalizations in the past when you have a square root in the denominator and you've been asked to multiply top and bottom by that square root, and they end up canceling each other out, and you're just left with an expression that does not have a square root in the denominator. Well, this process is actually the reversal of that. In doing that, you're adding extra factors into top and bottom, and when they're binomials that involve radicals, that extra factor is what's causing the 0 over the 0. So we have to kind of undo that process here. So to do that, we will take the original expression, and we are going to multiply top and bottom by a binomial. And that binomial is the conjugate pair of the numerator. So remember, conjugate pair is like the other half of difference of squares. So they have the exact same terms as the numerator, square root of x and 2, but instead of being minus in between, it will be plus. By multiplying by the conjugate pair, what that results in is the numerator is difference of squares. So we square the first term, square root of x squared is just x, minus the second term squared, 2 squared is 4, leaves us with an expression that does not have the radical in there anymore. And what will almost always happen is this expression that's left in the numerator is going to be a common factor or a related factor to the original denominator. So in the denominator, I'm not actually going to multiply any of this out. And I suggest you guys don't either, otherwise this makes it a lot more complicated. Because now that I see the result of the numerator, I see that these factors just simply cancel one another out. So because I canceled out the entire numerator, remember there's a 1 left up top there. So this gives me, I kind of ran out of space here, but this gives me our new form of the original function that I can now evaluate the limit at. So the resulting expression is 1 over the square root of x plus 2. So now if I try plugging 4 in, I get 1 up top. Square root of 4 is 2, plus 2 is 4. So that is the value of the original limit, not the indeterminate. So when this happens, when we get indeterminate form, we fix it and then end up with a limit. Again, what that's describing is a hole. This function has a hole at the coordinates x equals 4, y equals 1/4. All right, let's try another one with radicals. So if I plug x equals 2 into this function, in the numerator, I get 1. As soon as the numerator is a non-zero value, you know for sure that you are not headed down the indeterminate track. This is either going to be a numeric final answer or it's going to be one of the infinite results where it's a number over 0. So that's one really nice thing to keep in mind. So again, try to avoid doing extra work that's not totally necessary. So in this case, 1 up top and the bottom, 2 minus 1 is 1, square root of 1 is 1, plus 1 is 2, and our final answer is simply 1/2. That's it. All right, next one, some trig problems now. So limit as x approaches 0 of sine of x over tangent of x. So again, direct substitution. Sine of 0 means on the unit circle. If I rotate to an angle of 0, which is on the positive x-axis, what is the y-coordinate there? Well, the y-coordinate there, or the coordinates there are 1, 0. So sine of 0 is 0. Tangent of 0 means what are the ratio of the y over x coordinates at that angle, so or the slope. Well, that's a flat line, so the slope is 0. So once again, indeterminate form. This is where your trig identities come into play. So you do have to be an expert in some of our trig identities. One of those trig identities is our tangent function. So if you remember, tangent is the ratio of y over x coordinates because one of our identities says tangent is equal to sine over cosine. So I can take the original big fraction and rewrite it as sine of x divided by sine of x over cosine of x. And remember, dividing by a fraction is like multiplying by the reciprocal. So this is like we multiplied sine by cosine over sine, which in turn allows these sine of x expressions to cancel one another out, and it leaves us with cosine. So an alternative or equivalent form of sine over tangent is simply cosine. That we can evaluate at x equals 0. We know from what we looked at earlier that that is equal to 1. All right, our next one, limit as x approaches pi over 2 of 1 plus cosine over cosine squared. So pi over 2 on the unit circle, that's up top here. Coordinates are 0, 1. So when I plug pi over 2 in, I get 1 plus cosine of pi over 2, or 1 plus 0. So again, that top is 1, so I know for sure this can't be indeterminate form. So we get a break from the identities. But then the denominator, cosine squared of x, would be 0 squared, or 0. So this is, again, a non-zero number over 0, which is going to result, I mean, that was a really bad infinity. Another bad one. Yikes, only getting worse. So that is our final answer here. So this graph must have a vertical asymptote at pi over 2. All right, our next one, limit as x approaches 0 of absolute value of x over x. So direct substitution would be 0 over 0. So this is a unique one. So absolute value functions are unique because they themselves are piecewise defined functions. We just don't always write them as that. But the big issue here is there's no factoring no rationalization. There's no algebraic manipulation to be done in its current form. So instead, we have to do something unique here where we're going to take the absolute value function and define it as its piecewise. So remember, the absolute value graph is this v function, but really what it is it's parts of two linear functions. So to the left, or when x is less than 0, it is the function negative x. And on the right side, when x is greater than or equal to 0, it is the line y equals positive x. Well, if I take that form and divide it by x, what I'm really doing is taking each part and dividing it by x, which results in the new piecewise function. Negative x over x is negative 1 when x is less than 0, and x divided by x is positive 1 when x is greater than or equal to 0. So when we think about that graph, to the left of 0, we are at the y value of negative 1, and to the right of 0, we are at the y value of positive 1. So using the graph, we can evaluate the limit as x approaches 0, or try to anyways. And we see that this is a a jump discontinuity. There are limits. The one-sided limits are approaching different values, so we know that this limit does not exist. Our next one says limit as x approaches 1 from the right side of cosine pi x minus 1 all over natural log of x. So again, when we do these, even though this has a directional symbol on there, even though we're approaching 1 from the positive or the right side, we still want to attempt direct substitution first. So if I try that, I would get cosine of pi minus 1 all over natural log of 1. Cosine of pi, if you remember, pi is the left half, one half of the circle. So an angle of pi would be over here, and the x-coordinate there would be negative 1. Again, cosine asks for the x-coordinate of the angle. So we get negative 1 minus 1 up top. And then natural log of 1, that's like asking yourself, what power does e have to be raised to produce an answer of 1? So that would be 0. So we end up with negative 2 over 0, which again, any non-zero number divided by 0, that is really a form of infinity. And in this case, that would be negative infinity because of the negative 2 in the numerator. All right, and then for our last one, we've got the limit as x approaches 0 of x squared all over e to the x minus 1. So for this one, we can try direct substitution. That would yield 0 in the numerator, and then the bottom e to the 0 would be 1 minus 0 minus 1, also produces 0. So we have an indeterminate form. But this one, we don't have any algebraic techniques that would apply. There's no radicals, so we can't rationalize. Top and bottom are not both polynomials, so we can't factor. And there's no trig involved, so we can't really use trig identities either. So because of that, our only option would be to try and use a graph or a table to evaluate this limit. So I've got this guy plotted in Desmos. So when I take a look at this, so just rough eyeing it on the graph, it looks like as we approach 0 from the left and right side, we're going to approach 2. To verify that, we can build a table here. So I'm going to make this f of x1. So I plug these values into f of x up top there. So I'm just going to scoot the value of x closer and closer to 0. So I'm going to start on the left side. So negative 0.1, a little bit above 2, negative 0.01, so scoot it closer and closer. So you can see as I do that, I'm going to get closer and closer to 2. So that pretty much verifies what we thought it was going to be. But again, you want to do it from both sides. So let's do positive 0.1, a little bit less, and then positive 0.01 and 1,000th and so on. So you guys can see that as we scoot closer and closer, the y values in this case are in fact approaching a value of 2. So that would be the limit of this function. So there will be some problems for right now that our only option is to use the table or graph feature. Eventually down the road, we're going to learn another technique for evaluating limits, but that requires us to know a little bit of calculus first. So we'll be coming back for those later on.